Hello everyone. Welcome to one of our last deep learning seminar series of this term. So this week we have the pleasure of having Ziv Goldfeld. So Ziv's at Cornell, so I guess very soon he'll be tenured tenured professor. It's insider information. Yeah, and so Ziv is an information theorist. He has a bunch of papers, very cool stuff on quantum information theory, optimal transport, like obviously like machine learning theory. And today, he'll be talking about one thing that really caught my personal attention some time ago, which is exactly this Gromov-Wasserstein alignment, statistics, computation, and geometry. So all things that are, in my opinion, quite nice. So after you, Ziv.
Okay, thank you so much. Yeah, pleasure to be here and to give this talk. Thank you for the invitation. And yeah, hello everyone. Thanks for attending. First of all, if you have any questions throughout, please feel free to stop me and ask. I'm happy to take them on the fly. Yeah, and I mean, with that, like Anastasia said, I want to tell you a little bit about Gromov-Wasserstein alignment, which is this interesting setting that is rooted in optimal transport theory that basically asks the question of how to best match up probability distributions so as to minimize distortion to their internal structures. And I mean, I'll explain this in a bit. But I've been quite interested in this framework for the better part of probably 2.5 years now, because when I first encountered it, first of all, it had a bunch of applications to various machine learning, single cell genomics, computer vision tasks that have to do with aligning heterogeneous data sets. But at the same time, it didn't have basically any statistical computational theory associated with it, nor any geometric understanding of what's actually going on in the background. And I want to share with you today some nice recent advancements that we had in this space. And yeah, results that I'll present are probably spread across 4 different papers at this point with a wonderful group of collaborators. So huge thanks goes to Zhengxing, Christian, Yusuf, Barat, Gabriel, and Kengo. And with that, I'll get started. And I mean, the story really begins from optimal transport theory that kind of sets the baseline here. So let me just say a few words about that. And I mean, in its core, optimal transport is really a question about comparing probability distributions by quantifying the total cost associated with transporting or reshaping one into another with respect to a given cost function C, where our ability is basically, or our flexibility is basically to decide how we move mass around. And I mean, this is an old problem that dates back to the 18th century, to the French mathematician Gaspard Monge, who originally formulated it as follows, where you can see that we're looking at this infimized total or expected transportation cost, where the infimum is over here over the set of all what we call transport maps, which are basically these strategies for how mass will be moved around, modeled by just deterministic functions from the x space to the y space that push forward our source distribution mu into our target measure nu, right? And I mean, I think this is quite intuitive. If you think about, let's say, Gaussians that differ by a shift, your transport map will just be a translation or something like that. And under appropriate regularity conditions, I mean, the Monge optimal transport problem is a very deep mathematical question with connections to PDEs, to fluid dynamics, to Riemannian geometry. But the main issue with this Monge formulation is that it doesn't really play all that well with discrete distributions in the kind of absence of smoothness. And we often care about the setting in the context of data, because first and foremost, transport maps between discrete distributions need not even necessarily exist, right? I mean, think about the simple example of transporting a point mass into kind of a half-half distribution on 2 points, right? You have to be able to split mass in order to do that, but deterministic functions do not allow for mass splitting. So in this case, the set of transport maps is empty. The problem is not even well defined, right? But even putting this aside and kind of thinking of this from a completely pragmatic perspective, we're looking here at a highly non-convex objective in terms of its dependence on this variable t that is optimized over a highly non-convex set. In fact, the set of transport maps is not even closed under any reasonable topology you can put on functions. And so, I mean, in this regard, Monge definitely had the right idea in mind, but to get something that works well with data, with discrete distributions, we need a little bit more. And it really turns out that the core issue here is this inability to split mass, which was addressed almost 200 years later by the Russian mathematician Leonid Kantorovich, that actually got a Nobel Prize in economics for his work on optimal transport. And Kantorovich's idea was to just relax this deterministic function requirement and allow stochasticity, allow randomized transportation strategies, which he modeled using this notion of couplings, right? So let me denote by this cap pi of mu nu over here, the set of all possible couplings of my two marginal distributions, where a coupling is just a joint measure on the product space that has mu and nu as its corresponding marginals. And up to that modification, everything is basically stay the same. We're infimizing this total cost of transportation, but this time over all these randomized transportation strategies as modeled by couplings. And I mean, this is the Kantorovich optimal transport problem, kind of the standard way to set up optimal transport these days. And maybe there's two things that I want to say about it. I mean, first of all, Kantorovich subsumes the Monge formulation as a special case. Whenever a deterministic function is optimal for a given transportation problem, Kantorovich will be able to recover that. But more importantly, you can observe that Kantorovich, in fact, serves as a linearization of the Monge problem, because we're now looking at an objective that is, in fact, linear in the variable pi, that is optimized over the set of couplings that is also defined by constraints that are linear in pi. So all in all, one big happy linear program, which immediately gives you computational tractability and loads of good structure for us to kind of employ and use for analysis. And in fact, a lot of kind of the advancements during the past 10 years or so in statistical and computational optimal transport are very much contingent on this linearity of the optimal transport problem. All right, so this is Kantorovich optimal transport. If there's any questions, I'm happy to take them. Otherwise, I mean, at this point, I want to kind of start thinking about optimal transport as a discrepancy measure between probability distributions. I think it makes sense, right? The more different your distributions are, the higher the transportation cost between them should be. And the object that makes this rigorous is that of the Wasserstein metric, which is arguably one of the most interesting objects in optimal transport theory. This is basically your Kantorovich optimal transport problem with a cost function that is now taken to be a distance on the underlying space, let's say the Euclidean space in our case, and maybe you raise it to the power of p and take a pth root of the entire thing to get something that behaves like an LP norm. And I mean, we don't call this a distance or a metric for nothing. Indeed, it metrizes the space of probability distributions with a finite pth moment. This is what this little subscript p over here represents. And this metric space we're getting out of it, which is called the Wasserstein space, one of its unique characteristics is that it actually entails a very rich geometry that is in many ways very similar to the geometry of the underlying space on which our distributions are supported. Again, for simplicity, let's say Euclidean space for us, because through this perspective, we can effectively kind of lift geometry over points, Euclidean geometry, to geometry over piles of points, which are basically probability distributions. Right? And let me try and give you a sense of what I mean by that. So, I mean, in the Wasserstein space, we can ask not only how far two distributions are from one another. I mean, this is exactly your metric, but we can also talk about the shortest path between them that connects them to one another and whose length is exactly this distance. We call these Wasserstein geodesic curves. And these geodesics give us a natural way to interpolate between distributions, kind of smoothly deforming the one until you reach the other. And I mean, this idea has a bunch of applications, for example, for shape morphing tasks in computer vision. Now, the moment that you have a geodesic, you immediately have a natural sense of an average between these two endpoints, right? That just the midpoint of the geodesic will be that average. And this idea can be extended to taking averages of large collections of distributions using what we call Wasserstein barycenters, which are very useful for various ensembling methods. And I mean, in fact, you can even optimize functionals of probability distributions, maybe an entropy or a loss function or some notion of energy over the Wasserstein space by running gradient flow algorithms, because the space in fact behaves almost like a Riemannian manifold, and in particular it has a fully differentiable structure that gives you access to this very powerful algorithmic framework. So I mean, of gradient flows. So, I mean, all in all, there's loads of good structure for us here to try and kind of exploit or tap into. And I think that because in modern data science, right, we often model complex data sets as probability distributions over high dimensional manifolds. Through this perspective, we can effectively think about various learning tasks as these abstract operations or manipulations of probability distributions in a suitable geometry. And using Wasserstein geometry, we can resolve such tasks in a very methodical and principled manner, because at this point, thanks to, like I said, I mean, 10 years of progress in statistical and computational optimal transport, we have accurate and efficient algorithms for computing all of these guys at scale on real-world data. And I want to give you kind of a sense of how this may look like, again, unless there's any questions that I can address at this point. Okay, so here's a simple example. Let's think about a task of mixed style transfer, right? Where I give you a content, I give you a bunch of styles. I want you to mix these styles and apply to the content. So I want a box that does maybe something like that. Now, if you try to, I mean, this is quite a complicated rule. If you try to just learn it in a black box fashion, throwing data and compute at it, there will be quite a bit of overhead. I mean, this is a complicated rule that we're trying to learn. However, using Wasserstein geometry, we can resolve it with two simple ideas from this geometric perspective. And in order to do that, we want to throw the problem into the Wasserstein space, which requires encoding our images, let's say, starting from styles into probability distributions. And I mean, there's a standard way to do that nowadays. I mean, for example, you can use pre-trained VGG networks and some layers, feature extracting layers from those in order to build such encoders. But I mean, this can be done. So I map my images, let's say the four styles, into probability distributions. And the first thing that I want to do is obtain my mixed style, which in the language of optimal transport and Wasserstein geometry is just my barycenter, assigning weights to each style, defining how intense it should be in the mixture. I learned the barycenter, which specifies this mixed style for me. There's no content here yet, so let's bring in the content. And now the goal would be to apply this mixed style to my content, which calls for a second idea from Wasserstein geometry. You just run a Wasserstein geodesic between the two, choose how much of the geodesic you want to traverse, and obtain a distribution in between that, when decoded back, produces the stylized content as we desire. And I mean, this is an actual system. This is known as Wasserstein style transfer. It was proposed in 2019 by a good friend of mine and a collaborator, Yusuf Murad. And this is just one tiny example in an ocean of kind of algorithmic innovation and creativity that was driven by this Wasserstein geometry perspective. So overall, again, very powerful framework that has played a pivotal role in recent developments, in recent algorithmic developments. But with all that being said, I mean, the Wasserstein geometry is not necessarily the right one to have in mind, no matter the task at hand. And at this point, I want to start kind of maybe surfacing some insufficiencies to start building towards Gromov-Wasserstein distances, okay? And a first simple example where Wasserstein distances don't quite fit the bill is the following. So consider that what we want to do is just interpolate between these 2 point clouds, right? These two horse shapes. Now, of course, we just talked about it. You can run a Wasserstein geodesic between them, sample points along that geodesic in order to obtain interpolants that look something like that, right? And I mean, it kind of interpolates, but at the same time, there's a bunch of artifacts here of essentially particles that are just flowing along the trajectory that minimizes transportation cost, right? What is the closest destination to my starting position that I can reach without any reference or preservation of the global structure? Because there's nothing about Wasserstein distance that incentivizes it to preserve or even look at global structure. And of course, this is not quite what we're looking for. If anything, we're looking to perform something that behaves like rigid body optimal transport and produces interpolations that preserve the global structure at hand. And again, Wasserstein distances don't quite do that for you. Another canonical situation where Wasserstein distances don't work is when you want to quantify discrepancy between probability distributions that live in completely different and incompatible spaces, right? And I mean, this is not a great example because, of course, I can put both of these in R2, for example. But I mean, think about two metric spaces with two different metrics defined on them, right? Different notions of similarity. There's not even a way to write out a Wasserstein distance or define it in that situation. Yet the question still stands. Is there a meaningful notion of discrepancy that we can employ in these types of situations? And what I'll show you is that both of these instances, as well as a bunch of additional ones, can be kind of holistically treated under the single canopy of an alignment problem, which is that of a Gromov-Wasserstein alignment. And that's what I would like to start talking about next, unless, again, there's any questions about any of the optimal transport stuff. Okay, so Gromov-Wasserstein. And well, alignment is really the standard way to motivate the setting where you want to learn a matching or a correspondence between heterogeneous data sets, which comes up in a bunch of applications, if it's object matching or shape matching in computer vision, or multimodal analysis of biological data in single cell genomics, or maybe matching up language models for machine translation applications, although this is kind of obsolete now that we have large language models. But I mean, there's various such applications that involve heterogeneous data where this framework comes in and is quite handy to consider. And in these applications, we typically care about two things. I mean, first of all, we want to quantitatively compare how similar or different my heterogeneous data sets may be. But more importantly, on top of that, we want to obtain the matching or the correspondence that nicely aligns them with one another. And the Gromov-Wasserstein distance is basically built in order to do both of these at the same time. So let me show you how, and maybe I'll use this object matching task as my running example here. So we want a correspondence between these two geometric objects, right? We want the correspondence to preserve global structures, so maybe kind of matching head to head, shoulders to shoulders, toes to toes, and so on and so forth, right? And as I mentioned, the data sets may be heterogeneous, so we might be actually looking at something like that. This is perfectly fine. And the first thing that I need here is a model for my geometric shapes themselves, for which I'm going to use metric measure spaces, where the metric space, x dx or y dy, effectively captures the internal geometry or the intrinsic geometry of each space, whereas the probability distribution maybe captures density or intensity of your particles or pixels or atoms or what have you, depending on the data that you're looking at. And with that, I can now go ahead and replace my geometric shapes and abstract them away using these metric measure space models, which is kind of nice because, of course, you can represent pretty much any data set that you care about in this very general fashion. That's ingredient number one. Next, I want my alignment, which in the language of optimal transport theory is just a transport map. Again, a function that would rearrange this blue mass into the red one. And I'm using functions here just for kind of simplicity of presentation. We'll switch to couplings a la Kantarovich in just a moment. But I mean, up till here, this all is quite similar to optimal transport, though here comes the key difference, which is how I'm going to define my cost function. And the idea is that because I want this t to serve as an alignment, we're going to impose a minimum distance distortion requirement on it, essentially asking it to preserve as best as possible the pairwise distance distribution, matching close by points in the blue world to close by points in red, far apart points in blue to far apart points in red. And all in all, we want this t to behave approximately like an isometry. And I'm going to set up a cost function that encourages or enforces exactly that by penalizing for distortion of distances that are induced by this mapping t. Okay, and I'm showing here the quadratic version of the cost. Of course, you can parameterize with other exponents as well. And I mean, I'll be sticking with the quadratic version throughout. So that's the one we'll be looking at. And if you're fine with these three ingredients, then really putting them together up to switching from mappings to couplings gives us our definition of the quadratic Gromov-Wasserstein distance, which is due to Facundo Memoli back in 2011. I think this even appeared in a slightly earlier conference paper in 2009. And at a technical level, you can see that what we're looking at here is an infimized L2 norm of the distance distortion cost with respect to this pi times pi product coupling over here. And I'll talk about this more in a minute. Whereas maybe kind of more interestingly, what really happens here at a high level is that you're quantifying the least amount of distance distortion you can achieve between your metric measure spaces while optimizing over all possible matchings thereof, which are again captured by these couplings. Okay, so this is the definition.
I have one question actually. So I'll try to ask the first question. Yeah, so like when if we contrast this to the Monge problem, you know, like the Monge/Kantarovich problem, yeah, when the optimal coupling is just like a push forward by some deterministic function, you know, yeah, does the coupling version recover like the function version, like the Monge version?
It's a great question. So actually, the Monge, this notion of Gromov-Monge maps, how we call them, whenever you have a deterministic function to solve this problem over here, we don't understand that the requirements for the existence of Gromov-Monge for optimal Gromov-Monge maps very well. There's only a handful of cases where we can actually say that a deterministic function is good enough for this task, and otherwise, this is one of the important open questions in this field. So, I mean, in the one-dimensional case, under certain conditions, when you look at discrete data sets, you can argue that permutations are good enough, so that's fine. There's slightly modified notions of distortion to consider. For example, if you consider inner products instead of metrics, then you can still do something and argue that Gromov-Monge maps solve the problem. But in general, this is a difficult question that we don't have a great handle over. So yeah.
I also have a follow-up question, if you don't mind. It's just to fully build my intuition, and I'm sure at least unless you have this one person in the audience has this question besides me, or something maybe related. Yeah. Okay. So suppose you consider the Gromov-Monge case just purely for intuition. Is it obvious that if such a thing exists, that it's necessarily by Lipschitz, or can it be like by Holder or something like this? Like, is the optimal thing necessarily linear distortion?
So again, like in terms of how much regularity do these solutions possess, maybe as a function of regularity of the population measures of the mu and u,
Mhm.
that's, this would be by analogy maybe to Caffarelli regularity theory for optimal transport. Again, we don't
Cool.
have much
No,
of
that's good.
this.
That's good. It's good to have okay,
Yeah,
interesting
no,
questions to
that this
solve.
is this is a
Interesting.
kind of new and upcoming field
Yeah,
with
yeah.
loads of open questions to consider,
Very cool.
and I'll be pointing out some of them throughout the talk. But yeah, you're bringing up excellent points, and
Cool.
unfortunately, maybe in 5 years
No,
I'll have
that's
answers.
fortunately. It's good to have one
Yeah,
question. Very
yeah.
cool. Thank you.
But yeah, so one thing I want to emphasize here, and this is actually the source of much of the uncertainty that we just discussed,
Mhm.
is that you can already notice at this stage that this objective over here is quadratic in the coupling, right? As opposed to
Mhm.
linear in the optimal transport case.
Mhm.
Why is it quadratic, by the way? Because I have to sample from pi twice to evaluate my cost, right? You sample once, you get xy, a point from each space. You sample for a second time independently, you get x prime, y prime, a second pair of points, one from each space. Now you can measure distances and quantify distance distortion. So we have to
Mhm.
sample twice, and therefore we have this quadratic nature. And in my humble opinion, this quadratic dependence on pi is to a great extent why, in particular, statistical and computational Gromov-Wasserstein has been almost completely stagnant for
Mhm.
more than or almost 15 years since the inception of this problem, while statistical and computational optimal transport was making strides and has seen a lot of
Yeah.
progress. A lot of what we know how to do in optimal transport case is contingent on this linearity, which is just not present
Mhm.
for the Gromov-Wasserstein
I
problem.
see.
And I mean, overcoming this challenge is one of the key things we'll have to figure out in order to start making progress. So we'll get back
Cool.
to this point. But I mean, yeah, this is the definition. Here I'm showing the more general parameterization where the Q parameter exponentiates the distances. The P parameter is for the LP norm. This is the PQth order Gromov-Wasserstein distance. And for those of you who are familiar, this is actually an LP relaxation of a slightly more classical notion of Gromov-Hausdorff distance that measures how far two metric spaces are from being isometric. And I mean, as such an LP relaxation, once again, the Gromov-Wasserstein distance right off the bat possesses some excellent structural properties. And I mean, first and foremost, in my opinion, it gives us a very robust and broadly applicable framework for now comparing pretty much any two data sets that you want. It doesn't really matter anymore. Euclidean data, graph data, manifold data, all of these can be compared. All of these are crunchable under this framework, subject to these mild moment conditions on the marginal spaces that would be satisfied by pretty much any data set that you will encounter in practice. So this is very useful. On top of that, the distance, in fact, nullifies if and only if there exists an isometric transportation map between our two distributions, which we can further understand in this distance with a bunch of symmetries and invariances, right? You can translate your distributions, you can rotate them. None of these will actually change your Gromov-Wasserstein distance measurement, which is again useful, for example, for learning symmetries or for graph isomorphism tasks, testing tasks, and things of this sort. And lastly, much like its Wasserstein counterpart, the Gromov-Wasserstein distance defines a metric on the appropriate space, which in this case is a quotient space, a space of equivalence classes of metric measure spaces that are identified up to this isometric relationship from before, which I mean, I think is remarkable because you start from this completely abstract space of equivalence classes of metric measure spaces, and all of a sudden you get metric structure, you get tools for analysis, you can start thinking about geometry. And I mean, admittedly, we don't understand as much about Gromov-Wasserstein geometry as we do about the Wasserstein one, but there is still loads of good structure here to kind of adopt this as a framework for alignment and try to maybe mold it into principal alignment algorithms and mechanisms. But for that, we have to start developing statistical computational theory, and for that, we have to figure out what to do with this quadratic dependence on pi. So let me address this question first. And the way we're going to go about it is basically we're going to develop a new variational form, variational representation for the quadratic Gromov-Wasserstein distance that will connect it to a certain class of optimal transport problems. And the moment that I will have this bridge between Gromov-Wasserstein, right, a new problem that I'm trying to understand, and optimal transport, a well-understood problem that I know a lot about, I will effectively be able to start kind of tapping into this pool of knowledge and use my statistical, computational, geometric optimal transport theory to make progress on the GW side of things. Okay, so that's the plan. I'm going to treat a special case, an important but a special case nonetheless, which is the quadratic distance and Euclidean metric measure spaces flat spaces. By now, by the way, we know how to extend most of this to Hilbert spaces and even to kernel GW over manifolds of constant curvature, but I will be sticking with this flat Euclidean space throughout. And here is my quadratic distance. Now, the nice thing about a quadratic cost is that you can expand it, right? And indeed, if I just expand it and collect terms, then up to this assumption that my populations are centered, which comes for free because of invariance to translations, we can now decompose our quadratic GW into the sum of two terms, where the first one is basically just a constant, depends only on the marginal distributions and contains these moment-like expressions you can see over here, whereas the second one captures the dependence on the coupling. Again, you can see the quadratic dependence in the last subtracted term. And of course, from an optimization or a duality perspective, it is only this S2 that is interesting. So that's what we're going to do, develop a variational form for S2 with the goal of starting from here and again, connecting it at the end to an optimal transport problem. Main challenge is that here I'm quadratic in pi, and I know that optimal transport is linear. So, I mean, we have to linearize, and I'm not going to do anything fancy. I'm just going to linearize as such, specifically by replacing this quadratic term with the following simple optimization problem. You can easily check that if you differentiate this guy, find the critical point and plug it back in, you go back to the original expression, right? And by further observing that this critical point, which I'm denoting by aij star of pi over here, specifically looks like half the correlation between xi and yj with respect to my coupling pi, then just by applying Cauchy-Schwarz inequality, I can further restrict my optimization domain to this bounded interval whose edge points depend only on the marginals, where this m mu nu is exactly the root of product of second moments, which pops out due to the application of Cauchy-Schwarz. And once we're here, I can now pull the infimum over aij's outside, rewrite everything in matrix form, where this dm mu nu set is the set of all dx times dy sized matrices that are entry-wise bounded by the same mu nu over 2 constant as before. And once I'm here, I'm actually in business. Because if we think about this expression under the integral as some new weird cost function, obviously parametrized by this auxiliary matrix A that we've introduced, then inside this dashed box over here, we have exactly an optimal transport problem with respect to this CA cost, which I'll be denoting by OTA. And this brings me to the promised variational representation, where I now have been able to write my second bit, this S2 bit in my decomposition of quadratic GW, as the infimum over a class of optimal transport problem with a parametrized family of cost indexed by these matrices A. So Gromov-Wasserstein is not optimal transport, but is the infimum of such, and this is more than enough, in fact, to start doing some statistics and computation. Any questions about this? All right, so let me show you what we can do with this. And I mean, I'll start from the statistical question because, you know, algorithms will predominantly run on sample data anyway. So you have to be able to estimate the distance from samples before doing anything else. And I'm really asking the simplest statistical question possible here, which is basically how good is the empirical plugin in approximating the ground truth distance between my populations, right? So you observe ID samples from each distribution, you build these empirical measures, you plug them in, and you hope to get a good proxy, maybe if your data set is large enough, of the GW distance between the two populations. And the question is whether this is indeed the case. And at least asymptotically, we know the answer. This dates back to Memoli's original work, where he showed that the empirical plugin is in fact an asymptotically consistent estimator of the distance between the populations. But the moment you take another step to the non-asymptotic regime and you ask, well, okay, but what is the rate at which this empirical error actually converges to zero? Well, this has remained a widely open question in the field, that thanks to this variational form that I just showed you, we can now resolve it and derive a sharp characterization of empirical convergence rate. So let me show you. This is my first main result. I'm showing here the upper bound. I'll say something about the lower bound in a minute, but I mean, in principle, this rate is sharp. You can see that I'm assuming compactly supported distributions. By the way, how to treat unbounded support, we don't know yet. So that's another open question here. My bound comprises two terms. The first one over here that converges at this n to the minus half parametric rate of estimation, n being the number of samples. This is basically a rate of convergence for this constant, for this S1 bit of my decomposition, plus a certain centering bias that I'll talk about more in just a minute. Whereas the second half of this bound, the more complicated term, the one that actually depends on dimension, This is your rate of convergence for S2. And the analysis of this guy is very much contingent on this variational form that I just presented. And maybe before I show you the main ideas behind the proof, let me just make a few more comments about the result itself. So first of all, I mentioned the rate is sharp. You can produce an example that shows that this is the best rate you can hope for. In general, nothing sophisticated. I mean, basically two uniform distributions over concentric balls over different radii will be able to show that, well, you have to suffer at least this much in terms of the estimation error. So I won't be getting into too much details about that, but just take my word for it. Maybe slightly more interesting here is the dependence on dimension. And first observation is that, well, curse of dimensionality occurs here, right? We have this exponential dependence on dimension sitting over here, and this is expected in these types of estimation problems. This is something that happens for Wasserstein and optimal transport cost estimation as well. So, I mean, it is what it is, I guess. But at the same time, do observe that it is the minimum of the two dimensions that actually enters the bound, which means that if you're aligning a high dimensional and very complex data set with a simple low dimensional one, it is this low dimension that will govern the rate, which is quite nice to know. That's as far as that. And the last comment, more kind of high level, almost at the level of pattern matching. If you actually compare this bound to the best available rates for optimal transport, you observe that the dependence on the various parameters is very much in line with one another, which is mostly to say that, at least from a statistical standpoint, estimating Wasserstein versus estimating Gromov-Wasserstein has a comparable difficulty, which is not at all the case for computation. So, I mean, just log that and keep it in mind.
Maybe I have just two pure curiosity questions, especially since you mentioned that there's like more general settings that you've considered. So what would dx or dy be for like a general metric space? Like, would it be doubling dimension, I guess?
What I refer to as we can extend to Euclidean spaces and to constant curvature manifolds is the variational form. Deriving the rates requires control over essentially regularity of dual potentials of these associated optimal transport problems, which at the moment we can only do in this quadratic setting. We can do sharply in this quadratic setting, and we can derive bounds for which we cannot prove corresponding lower bounds for general PQs.
I see. That's interesting. Cool. Cool.
All right. And maybe let me say a word about the proof. So, I mean, we mentioned that we have this decomposition of GW into S1 plus S2, so it makes sense to try and decompose the analysis as well. And you have to be careful here, because if you recall, the decomposition requires that distributions are centered, which you can safely assume about your populations, but this need not imply that the corresponding empirical measures are centered as well. So really what's hiding behind this inequality here is a centering step. You translate the empirical measures by the sample mean, then you can decompose, but one has to account for the bias that is introduced by the centering step, which ends up costing this extra n to the minus half additive factor on the right, which of course doesn't change the overall rate. So this is fine. And we can now decompose, at which point we can analyze each term separately. The analysis of S1 is very easy. It's just estimation of some moments of our distributions. You can do this with sample means, again, at the parametric rate. And together, these two highlighted terms give me the first half of the bound. And with that, the remaining question is, okay, what about the estimation rate for S2? And this is where the variational form comes into the picture, because it basically allows me to reduce this question to a question of estimating an optimal transportation cost, which I know how to do, up to the fact that we're carrying the supremum over the matrices A with us, just from how the variational form looks like. And this bound kind of suggests that, okay, I mean, whatever is the analysis we know how to execute for cost estimation of optimal transport, here we'll have to be able to execute it uniformly in this family of cost functions indexed by A, which introduces some additional technical overhead, but the family of costs is nice enough so that you can actually do that. And the key is that after applying my variational form and obtaining this upper bound, I'm in optimal transport land, a well-familiar territory where I have a bunch of powerful tools for analysis of these types of estimation problems. If it's duality-based proofs, if it's tools from empirical process theory, covering arguments, entropy integrals, and if it's even low-dimensional adaptivity properties of optimal transport cost estimation to low-dimensional spaces. And I mean, this is known, by the way, as the LCA principle, the lower complexity adaptation principle for optimal transport. This was something that was derived in Axel Monk's group in the University of Göttingen. And altogether, you put this machinery into action and you obtain this n to the minus d over the minimum n to the minus 2 over the minimum dimension, which combined with the other parametric rates produces this overall bound. So, I mean, I like showing this proof because I really think it nicely highlights the role of this variational form, which is basically unlocking this entire analysis by enabling me to start to think in terms of optimal transportation. All right, so that's as far as estimation rates. I wanna say something about slightly more recent results we have in the space of statistical optimal transport, because we started to think about just finer statistical questions, specifically this question of a limit distribution theory, which is very important for inference, for testing, for deriving confidence bands and stuff like that. And the idea is that you basically pull your empirical distance out of the expectation, you center it by an appropriate population quantity, you hit it by a rate, and you take n to infinity, asking whether a non-degenerate limit emerges as n grows. And these are usually quite intricate questions to address, but we've been able to do that in 3 important settings in this Gromov-Wasserstein framework. Discrete to discrete is when both my mu and nu populations are discrete. Semi-discrete, one is discrete, the other one is continuous. And we also treated the fully general case of 2 general sub-Weibull distributions, but when the distance is regularized by an entropic penalty that I'll talk about more in the computational bit. And really, the common denominator of these 3 settings, which is why we've been able to treat them, is that in all 3, you can show that the underlying empirical process converges weakly to a Gaussian process in an appropriate function space. And once you have that, we have in the group kind of a well-developed methodology for how to lift this weak convergence of the empirical process to convergence of the functional of interest. And this is how it works. I mean, we have the weak convergence. At that point, you want to basically run through a stability analysis of your functional. So you, in particular, derive its Gateau derivative, as well as prove that it is Lipschitz with respect to the sup norm that is induced by this function class. Usually this is a class of some dual potentials of the associated optimal transport problem. And once you have that, you basically get access to the extended functional delta method that allows lifting the convergence of the underlying process to the convergence of the functional with the same root n rate, where the limit usually looks like a Hadamard directional derivative of your functional, which coincides with the Gateau derivative in this setting, evaluated at the limiting Gaussian process. Okay, so I mean, there's a standard approach for doing this stuff. And again, it's the connection to optimal transport that allows going through this entire analysis. And maybe, I mean, I'm not going to go into any more details on this, but just another kind of nugget of a fun fact that I like about this project, and here is the archive link if you want to check it out, is that something very interesting happens in this discrete to discrete case. Because, I mean, you first run through this analysis, you end up with a limit that has some horrible structure of an inf and a sup and some functional of some Gaussian variables, but you can then massage it and show that it's actually equivalent to a solution of a linear program with random Gaussian coefficients. Which can be, which first of all, I think is kind of surprising that a sequence of quadratic programs converges to a linear program, something linearizes in the limit. But from a practical perspective, we can efficiently simulate this LP in the limit and actually use it for applications. And indeed, we present an application for testing whether 2 random graph models are isomorphic to one another based on IID observations from them. And all in all, I think this is kind of a very compelling framework for statistical inference. And I encourage you to take a look if this is interesting to you. Okay, but this is kind of as far as I want to go in terms of statistical optimal transport. And at this point, I want to switch gears a little bit and talk about computation. Again, unless there's any questions that I can take about the previous part. We're good?
I had a question, but I think it's good.
All right. Yes. Hi, Rob.
Quickly, does this duality argument extend to, let's see, other cost functions that allowed us to transform Gromov-Wasserstein to standard optimal transport? Like, could you do some kind of C duality for general costs, or
so
I don't know.
which dual are you exactly referring to? My variational form?
Yeah.
Yeah. So the
Like, do we
variational
expect to
form,
do that in general?
yes. I mean, you can derive such a form for general PQ cost. I think when I mean, definitely for even parameters, because then you can still expand kind of the cost function and obtain a optimal transport problem with respect to a cost that has some, has some polynomial terms in it with an order that will go as high as p times q, I guess, which would be the highest order term. So you can do that. but this doesn't give you sharp statistical rates, for example, at least not that we can pinpoint. You can even do this in Hilbert spaces where, instead of optimizing over functions, you'll have some operators in play, but a similar type of analysis will go through if you're looking not on Euclidean metrics, but metrics that are norms, but norms that are induced by an Hilbertian structure. Yeah.
Cool. I think I forgot the expansion. That makes sense. Thanks.
Sure. Yeah. All right. Okay, so let me say a few words about computation. And from a computational standpoint, Gromov-Wasserstein is actually an instance of a QAP, a quadratic assignment problem, which is a hard non-convex optimization problem. In fact, it's NP hard, NP complete even. And I mean, this fact has motivated folks to look at a bunch of, computationally tractable reformulations and relaxations of the original Gromov-Wasserstein framework. And among these, the most popular one is probably that based on entropic regularization, where as per usual in optimal transport, we regularize, in this case, our distance distortion cost by the scale divergence penalty on the coupling versus the product measure mu times nu. And I mean, the motivation or the inspiration to do that comes actually from optimal transport, from computational optimal transport, where this strongly convex scale divergence regularizer in the coupling pi actually serves to convexify the originally linear optimal transport problem. And then you can solve this regularized problem very quickly using sinkhorn fixed point iteration algorithm, which was a brilliant observation by Marco Couturi from back in 2013. However, I mean, things are not as nice in the Gromov-Wasserstein setting because our original functional is not linear. It's rather quadratic, non-convex. So, I mean, this entropic penalty doesn't convexify it as such. But thankfully, there was still enough structure there so that folks were able to derive various heuristic algorithms for approximate computation, if it's based on kind of recursive runs of the sinkhorn algorithm or mirror descent type approaches. And I'm calling these algorithms heuristic just because of none of them had any convergence guarantees, let alone convergence rates associated with them. And this is, again, the gap that I would like to close, which we can do using this variational form, which holds just as well in this entropic setting. I mean, you basically absorb the regularizer into optimal transport and end up with entropic optimal transport as opposed to optimal transport as before. And because S1, again, is just a constant you can compute offline, the question is how to solve this minimum over A of this entropic optimal transport cost problem over here. And to get a sense, let's give the objective a name and start by, again, studying stability to try and get a sense of how nice of an optimization problem we're dealing with here. And what we can do in this regard is actually characterize the first order Fréchet derivatives of this subjective phi. I mean, morally, you can think of these as a gradient vector in a Hessian matrix of this map, and then further get a handle over the spectrum of this Hessian. And the moment that you can control the spectrum, it's basically a mean value theorem type of argument that allows you to show that this objective is in fact L smooth, meaning that it has L Lipschitz gradients, which immediately gives you access to first order methods with convergence rates, with at least local convergence guarantees. But if you even have convexity, this can be upgraded to global guarantees. And speaking of convexity, the moment that you have a lower bound over the smallest eigenvalue, then just guaranteeing that this guy is strictly positive yields a simple primitive condition on the regularization parameter epsilon that if holds, you actually get strict convexity of this objective. And then, as I mentioned, I mean, all your local solutions get upgraded to global ones. But I mean, regardless of whether your epsilon is large enough or not to satisfy this condition, you always have smoothness. So you can always employ first order methods. And this is exactly what we're going to do. Specifically, I'm going to essentially propose an accelerated first order method with an inexact oracle, which is kind of a mouthful. So let me try and unpack what's going on here. And I mean, first order methods suggest that I need a gradient. I mentioned already, I have gradients from the previous computation. And this is how the gradient of this objective looks like when at the current point A. And in particular, we can notice that it depends on this pi A over here, which is the optimal coupling for this entropic optimal transport problem with the cost specified by the current A matrix. And I mean, the moment you see that, the first idea that comes to mind is, well, great, I'll just run sinkhorn algorithm to solve this entropic optimal transport problem. We'll get some proxy optimal coupling for this pi A, plug it into my gradient formula, obtain an approximate gradient, swipe the error due to sinkhorn under the rug, and proceed as usual. Okay, but I don't want to swipe. I don't want to swipe the error. I want to model it. And this is exactly what I'm going to capture as my inexact oracle. Okay, so sinkhorn is my inexact oracle. I query it with a matrix. It gives me back a proxy optimal coupling, call it pi tilde a. I'll assume that it is within some delta precision parameter from the true optimizer pi a. And I mean, you can make this delta as small as you like, just run sinkhorn for long enough. Once you have that, we plug the proxy coupling into the gradient formula to get a proxy gradient. And from here, just proceed taking steps along these proxy gradients with the appropriate momentum corrections, hence accelerated gradient method up until convergence, at which point, by the way, you get not only a value for your entropic Gromov-Wasserstein alignment cost, but much like sinkhorn, you get an approximate coupling. You get an approximate solution, an alignment scheme, which is, again, the object that you usually want to get your hands on in practice. So this is quite useful. And I mean, on top of that, thanks to beautiful work that was done by very smart people in optimization theory and analyzing such accelerated gradient methods with oracles, we can actually, for the first time, get guarantees for this scheme. And I'm showing here the version for the convex case. This is building on a work by Desprémont in 2008, where, again, assuming implicitly my condition on epsilon, whence my objective becomes convex, the theory by Desprémont can be lifted to this Gromov-Wasserstein setting to provide a bound on the global optimality gap. And again, I have a bound with two pieces to it. The first one over here depends on k, which is my iteration count. And you can notice that it scales like 1 over k squared, which is your optimal Nesterov rate for smooth constraint optimization. So, I mean, you cannot do better than what this first term allows you to do in terms of dependence on k. Whereas the second expression, this is basically your cost for the inexact oracle that you can notice scales linearly with this precision parameter delta. And I mean, if you don't have convexity, all of this still goes through, just that you get local guarantees quite naturally, building on a framework by Gadimi and Lan in 2016. And the only thing that I want to say about this non-convex yet still smooth regime is that the Gadimi and Lan algorithm has a very nice adaptivity property to it, which is, I mean, it doesn't a priori require that your objective is convex, but if it happens to be convex, even if you didn't know that, the algorithm can adapt to that. You get a certain acceleration in terms of the rates, and of course, you end up converging to a global solution. So that's as far as the algorithmic story. Here's a quick numerical comparison. So I'm comparing our fast gradient method in terms of its overall runtime versus the size of the problem. How many points are we computing Gromov-Wasserstein on across different dimensions? And the comparison is to this mirror descent approach by Perrier-Couturier and Solomon from 2016 that for years was the go-to computational method in this space. And you can see that there's a full-blown order of magnitude improvement here. I can quickly explain why. Because, I mean, we are solving the problem in this dual auxiliary matrix space, right? Where every gradient step requires a call to sinkhorn, whose complexity is quadratic in the size of the problem. And this is what ends up dominating the behavior in our case. Now, the mirror descent approach from Perrier-Couturier and Solomon did not have this variational form to employ. And so they effectively solved the problem in its primal form. And this requires at each iteration a certain cost tensor update step whose complexity is cubic, which ends up dominating the runtime in their case. I do want to mention that in late in 23, came out a nice refinement to this mirror descent approach that can leverage a certain low-rank structure of the problem if indeed present. And under these low-rank assumptions, they can basically shave off one of these n factors and make it a dimension-dependent factor, at which point they recover the quadratic scaling that is empirically comparable to ours. But I mean, our algorithm is still the only one with formal guarantees. So in applications where this might be important, this is something to keep in mind. Okay, so this is my spill about computation. Any questions?
No, I mean, maybe just a curiosity, you know?
Right.
Yeah, so if you send epsilon to 0, or like, I guess, yeah, is there any guarantees that you recover the true, the true transport
so
plan?
you can actually show that you know, if you take, for example, the a sequence of vanishing epsilons, and you solve this problem for each of these epsilons, and you retrieve a coupling, then up to a subsequence, you will get with convergence to an optimal solution of the unregularized problem.
Okay. Yeah. But like follow-up question, because it sounds like what's it called, like a gamma convergence argument, maybe? Like
it's exactly that.
Okay. Then I know the answer to the next question. Cool. Thanks.
Okay. Very good. All right. So how much longer do I have?
Oh yeah, I was about to poke you. It's about, let's say about 10 minutes. More
10
accurately,
minutes.
maybe about 8 because I asked a lot of questions.
Sure. Okay. So
Sorry.
let me talk a little bit about Gromov-Wasserstein geometry. I personally love this part, and some of it might be a bit technical for folks that are not familiar with these ideas for the Wasserstein case. But I mean, I'll try to parse them as much as I can, and at the end, I'll show you some visuals that should make sense regardless. And the idea is the following, right? If Wasserstein geodesics are curves in probability space along which transportation cost is minimized, then Gromov-Wasserstein paths should be ones along which shape distortion is minimized, which sounds like a useful idea that, is worth some exploration. But because we a priori don't know what is the, let's say, Riemannian structure that induces this Gromov-Wasserstein geometry, drawing inspiration from how these ideas developed in the Wasserstein case, we're actually going to start from a gradient flow question, because oftentimes when you can characterize gradient flows, you can kind of eyeball the solution and extract the Riemannian metric tensor out of that. And the reason to start from gradient flows is because you can in fact think about gradient flows without ever knowing how the gradient actually looks like, thanks to proximal point method, thanks to implicit schemes, which is what we call the JKO scheme after Jordan Kindler and Otto in the case of optimal transport. And I mean, it is their famous result from 98 that as you shrink the step size of this proximal point method, it actually instantiates a W2 gradient flow. And therefore, with this in mind, our idea was very simple. Okay, we don't know how the gradient with respect to Gromov-Wasserstein looks like, but I mean, we can still do this. Just replace Wasserstein with Gromov-Wasserstein and see what happens. And you can see that, well, I'm using a slightly different variant of Gromov-Wasserstein distance. This is known as the inner product GW distance, the one that I mentioned before. Actually, one of the reasons to use it is because we have access to maps in this case, although since then we've figured out how to generalize this analysis to a full-blown GW distance. But let me stick with this inner product version. Again, can be understood as minimizing maybe angle discrepancy in this regard. And by observing that this IGW distance is in fact invariant to orthogonal transformations, this framework really makes sense when your objective has the same type of invariance. So we assume an objective with orthogonal invariance, and upon picking an initial distribution mu naught and taking your first JKO step, effectively solving this variational problem with the current mu naught in mind, you quickly realize that there's actually quite a bit of freedom here, because you don't end up with a distribution. You end up with an equivalence class of distributions, an orbit, if you will, of distributions along the orthogonal group. And while you in principle can pick just an arbitrary representative from this class, this is problematic in two ways. First of all, in terms of analysis, it's very hard to get a handle of the relationship between the previous JKO step and this arbitrarily chosen representative. But I mean, on top of that, maybe from slightly more kind of pragmatic standpoint, we wanted to end up with a sequence of distributions, not a flow of equivalence classes, which is also very interesting. But I mean, we wanted to be able to kind of interpolate distributions in this new geometry. And therefore, in order to get a specific distribution out of this class, what we do is that upon picking an arbitrary representative, we apply a certain orthogonal covariance transformation to it. Orthogonal transformation means that it doesn't change the objective, it doesn't change the IGW value, but it is built in order to best align this orthogonally transformed arbitrary representative with the previous JKO step in the W2 sense, in the Wasserstein sense. We want to get control over the Wasserstein gap between these consecutive steps of the scheme. So you pick a representative, you rotate, and take your next JKO step from there. And this is really how this IGW modified JKO scheme looks like. You interleave these orthogonal transformations with the JKO step. So upon rotating, you take another step, pick a representative, rotate, and proceed as follows. And you can see just from this illustration that while the red sequence here is quite irregular, I mean, this could be hard to handle. For the green sequence, we have control not only over the IGW gaps, but also on the Wasserstein gaps between consecutive steps along the algorithm, which basically allows us to analyze the scheme and get a characterization of the continuous time limit as the step size parameter vanishes. And this is this main result. Maybe we don't have to delve too much into the details here, but let me quickly try and explain what's going on here. So here is my JKO sequence for IGW. As I shrink the step size to 0, it converges to a W2 continuous curve because of these rotations that we've applied, mu t, that first of all follows what we call the continuity equation in the theory of Wasserstein geometry. Basically just a PDE that describes the fact that this flow is continuous with respect to the W2 distance. But more importantly, the evolution of the flow is governed by this velocity field over here that looks like some negative inverse operator acting on this gradient of the first variation of my functional, of my objective, which happens exactly to be the Wasserstein gradient. So it's effectively some inverse operator acting on the Wasserstein gradient of this objective. And the operator here is worth understanding. This is what we call the mobility operator. It is basically an operator that, well, let's see. It maps L2 velocity fields to L2 velocity fields. It's linear, it's self-adjoint, it has a finite spectrum. But more importantly, you can observe that it has a certain globality to it, meaning that even a single direction of the output velocity field is determined by looking at the entire velocity field at the input, which is very much in line with the global flavor of Gromov-Wasserstein distances. And if you explore this operator a bit further, for example, just consecutively apply it on some given vector field, you can see that what happens is that along the applications, angle discrepancy is eliminated. I mean, you try to just match up these angles as much as you can, again, very much in line with the structure of the cost of the Gromov-Wasserstein distance we're working with. And all in all, what this gives you is a movement or a flow in probability space whose action is to reduce the size of your functional, but along a trajectory that minimizes distortion to the global shape. Particles that are close at the beginning should stay close throughout. And just to connect it back to Wasserstein gradient, I mean, yeah, those of you are familiar, this gradient of the first variation of f is exactly the Wasserstein gradient of that functional, and therefore, at least formally, we can now characterize or identify the IGW gradient as this inverse mobility acting on the Wasserstein gradient. So the mobility operator is kind of the right tilt or the right modification to the Wasserstein direction descent or ascent, I guess, if this is a positive gradient, such that to steer you away from distorting the shape. That's basically what's happening here. And once we can characterize the gradient, again, drawing inspiration from autocalculus effectively, we can, like I said, from that extract the Riemannian metric tensor that gives rise to the intrinsic GW geometry. This is how it ends up looking like. And once you have the metric tensor, you basically have access to a dynamical formulation a la Benhamou-Brenier, which is basically an interpolation, allows you to interpolate between distributions in this new geometry. And I'm not showing the formula here. I mean, it's basically an integral over time of this metric tensor along a optimal trajectory. But I do want to show you some visualizations. So here's a first simple example. I'm interpolating here between a fat ellipse and a tall ellipse. On the left, we have the Wasserstein interpolation that you can see, I mean, just kind of effectively kind of smushes the fat ellipse into its tall position. Everything moves in straight lines like you expect it to for the Wasserstein case. The shape gets completely distorted. I mean, at some point, we pass through a perfect circle along the way, and that's what you get in that case. Now, in the Gromov-Wasserstein setting, you're not allowed to distort the shape, right? The distance tries to preserve the global structure, and therefore it automatically identifies the rotational symmetry and the rotation as the structure-preserving trajectory to interpolate between the two ellipses. And I mean, automatically is the key here, right? We don't tell it that there is a rotation. It's just the profile of this distance that tries to avoid distortion that pins this down by itself. And these are, by the way, the velocity fields that describe the movements. You can see exactly the two actions. The same continues to hold for more complicated shapes. So this is a cat versus a rotated cat. Wasserstein basically rips it apart and puts it back together at the end. Gromov-Wasserstein maintains the shape throughout the entire trajectory. I think this has natural applications to video interpolation, stuff like that. So this is definitely very useful. What I want to end with is something that I think is equally interesting, but I don't know what it is good for. So if you guys have ideas for applications, I would love to hear, which is the actual gradient flow. Let's look at the gradient flow for a minute, right? And this is for entropy, which has the right invariance properties, and specifically we minimize negative entropy, so you can think of it as maximizing Shannon's differential entropy. At the bottom over here, I'm showing the Wasserstein gradient flow. I initiate again with particles along the circumference of this ellipse and flow to maximize entropy, which looks like this explosion, everything flies off to different directions, and that's what you get, right? Basically a diffusion. For the IGW case, which is shown over here on top. Once again, along the trajectories, particles that are close at the beginning should stay close throughout, and therefore we still see that entropy increases, but in some more controlled manner, where me and my neighbors diffuse, but within each other's vicinity. And in fact, we can show that this movement can be decomposed into two components: a descent component, whose job is just to reduce the value of the functional, and a damping component whose job is to steer you away from distorting the shape. And it is the sum of these two that gives rise to the entire movement. And again, I mean, what this might be good for, maybe some controlled sampling or something like that, I'm not sure. I'm sure that there are applications, but yeah, we still are looking for them at this point. Right, and that's basically all I have. So maybe just to quickly summarize, so we've talked about this Gromov-Wasserstein alignment problem, which is very useful for aligning heterogeneous data sets in various different contexts. But yeah, even now, right, it's still lacking in many important aspects of statistics, of computation, of geometry, and even more basic things than that. In this work, we've been able to make some progress, specifically starting from this variational form that gave us the connection to optimal transport, which was the key ingredient for all the results that follows, this ability to start thinking in terms of optimal transportation. And we did some statistics with it. So empirical rates and limit theorems derive these first order methods for computation, and even made some progress on geometry in terms of gradient flows, Riemannian structures, and dynamical forms for interpolation. These are the papers that I covered. And with that, guys, this has been a blast. Thank you for listening. If you have any questions, I'm happy to take them.
Well, thank you very much. It's a very, very nice talk, I think. I have maybe one, welcome. I have maybe one question, but let's just check. Does anyone in the audience have any questions? Okay.
I just have one question. In the sample complexity of GW, the upper bound, I mean, there was a notation like dx, like wedge dy, and you said that it's minimum dimension, right? So I mean, I just want to know about that notation. That's all. I mean,
Sure. So what is the? Let me go back there. Almost. Bear with me. Yeah. What's the question?
Yeah, dx wedge dy you wrote in the denominator, right? Yeah. So what is that wedge? I mean,
oh, this is just a shorthand for minimum.
On the upside down one, what about that?
Max.
Sorry? Oh, and this is a maximum.
Okay. Oh yeah, that's all I want to know. I think.
Yeah. So I mean, apart from the case where you are in dimension 4, I guess, in this situation, then this is the right rate. In the high dimensional regime, this is the right rate. Even in optimal transport, the case, I think, of dimension 2 is still open. There's some logarithmic gap between the best known upper and lower bounds, something weird. So you have, in one dimension, the rate is n to the minus half. You cannot hope to do better than that. That's basically like a central limit theorem argument in the background, right? Or a Cramér-Rolle lower bound. So dimension 1, you have parametric rate. In dimension D, when D is large, let's say for Wasserstein, the rate usually looks like n to the minus 1 over D. And dimension 2 is there's this logarithmic gap because something weird happens on the plane, and this is also reflected in this result over here. I'm looking at square distances, by the way, which is why everything kind of looks squared.
Yeah. All right, can I ask another question? I mean,
sure.
Just in the probability space, the existence of the geodesic, which is the metric, is defined by the Wasserstein metric. I mean, I don't know. Is it has anyone proved that there exists such a geodesic between any two probability measures?
You mean the Wasserstein geodesic?
Yeah.
Yeah. The moment that you have finite second moments, which means that you live in the two Wasserstein space, between any two distributions, you can think about the Wasserstein geodesic. It's actually very simple to describe as well. I can tell you exactly how it looks like if you want. So let me just go back to this original picture that I had. Blah, blah, blah. Yeah, here, right? So what is this geodesic? So the geodesic is a sequence of distributions parameterized by time. Maybe time goes from 0 when you're here to 1 when you're here, right? And what sits in between? So take your mu and nu, solve the Wasserstein distance between them. It's not hard to show that there always exists an optimizer. So take an optimal coupling, right? Now this is a coupling of two variables, call them x and y. X marginally follows mu, y marginally follows nu, but pi gives you a joint distribution, right? And now consider the random variable, call it maybe xt, that looks like, maybe I can write, right? Now consider the random variable xt that looks like 1 minus t x plus ty, where your pair xy follows an optimal coupling for this above problem, right? And run with this t from 0 to 1. This is exactly the geodesic that you see here. This is also known as McCann's displacement interpolation.
Who is Canadian?
Who is Canadian? Yeah, who is in Toronto? And I met him last week in a workshop
Really?
in Colombia, and yeah,
Cool.
we had some interesting discussions about this stuff.
Okay, because generally we use the nabla connection to, you know, I mean, the general definition of geodesic is just the covariant derivative of the lambda dot is 0, right?
That's
So,
for Riemannian manifold though. But if you want, maybe during you can come to office after Hussein if you want. I can give
yeah,
you
okay,
some
sure.
references.
Yeah.
Cool.
Thank you.
So maybe just, I mean, this Wasserstein metric space is in fact a length space, right? And you can
Basically.
define the W rectified distance in the standard way, right? As supermove over partitions and so on and so forth. And I mean, this ends up coinciding with exactly with this geodesic that I described over here. So all of this can be made rigorous and compatible with your standard definitions that you're familiar with. And yeah, despite the fact that, I mean, the Wasserstein space is almost a Riemannian manifold. It's not quite because it doesn't have a constant dimension. But yeah, apart from that fact, everything else that you know about Riemannian manifolds holds here as well.
All right, thank you.
Maybe I just ask one quick question. Well, it's an idea. I don't know. So like a lot of the trouble seems to come from this non-linearity, if you will, of the interaction with pi. Has anyone ever considered weak Gromov-Wasserstein distance? Because now usually weak OT is used to solve these kinds of like non-linearity problems with classical OT. You know?
Yeah, it's a great point. The answer, I don't think it was considered.
Interesting.
So weak, yeah, you're not referring to linear. I think linear GW was considered.
No, weak I mean in the sense of like disintegration, and then you know.
Right. Yeah. I don't think this was explicitly looked at, but you're basically suggesting like to look at kernels, at transition kernels instead of deterministic functions.
Yeah, sure.
Yeah, I mean, I think this would basically coincide with the coupling perspective, right? Because I mean, your coupling can be decomposed into your marginal times the kernel, right? So like you can optimize over the kernel subject to having the right second marginal, and the pi over here would be replaced with something that looks like that.
Yeah, something like this. Yeah.
Yeah, I think this could be done. I don't know if this was looked at, but I would expect that you could prove like an equivalence between the two formulations. Yeah, but
no, I only ask because like I know usually like whatever. Basically, the weak OT community is like works on some problems, but it's very, really small. So usually people don't interact with it, you know?
Yeah.
So I'm just
No,
throwing
it's a good
that out
question.
there.
I think this would be interesting to look at. By the way, another variation you can consider here to like linearize this in some sense is that instead of working over these original spaces and sampling from the coupling twice, you can kind of consider a setting where you work over product spaces.
Yeah. I was thinking that too. I didn't want to ask it when you put the
and you
slide
have
on.
product measures, and okay, you need to extend the metric to the product space in the standard way.
Yeah.
And then you can just like look at a single coupling between these pairs, right? An x and x prime that follow the product mu times mu, y prime. You can do that. This
Why
would
not
linear.
though?
I think
Okay,
this is kind of an interesting thing to think about, but it gives you some like unfair flexibility in how you choose the points, right? Because like the coupling now, when choosing the y, sees the previous x, and I mean you can kind of hack it a little bit. So this is the standard framework for alignment. I completely concur with you that variations of that perhaps kind of have built-in linearity would be interesting to explore. To the very least, if only to understand their connections to this guy and if they can inform anything about the standard framework. Yeah.
Cool. It's very interesting talk, actually. Okay, I'll read some stuff, and if anything comes to mind, I guess I'll send you an email.
Excellent.
But
Sounds
thanks
good.
a lot,
Yeah, thank you
actually.
for having me. This was great.
Yeah.